who's not here in person, but is still an integral part of this presentation. We are Team 14, and we are so excited to present to you soft robotic for injury prevention. The problem we're faced with is that there are various risks of falling for routinely active people as well as elderly people. This can create a loss of sense of independence in completing basic activities, and there's currently no FDA-approved wearable soft robotic for injury prevention. We know that forward and sideways falls cause the majority of moderate to severe injuries and majorly impact people above 65 years of age. Falls and outstretched hands are the cause of over 90% of wrist fractures. So knowing this, we wanted to create an easily wearable modular device which protects different joints and muscles. We see a necessity to build an injury prevention system for our target users. Our client, Professor Russo, gave us a goal to create a safe, reactive, soft robot that will serve as proof of concept for protection here. And our overall goal is to deliver an everyday use, modular, wearable soft robotic that is able to prevent injury during user falls and thus bring a sense of independence back to at-risk users. So with our goal in mind, we conducted some research to figure out some current market solutions available. The first was hip protectors, vest airbag, as well as the motorcyclist inflatable jacket. We created a compute chart to compare the different aspects of these solutions available, with the most important criteria being the protection provided and its reliability. The result of our view chart was that the best airbag best mirrors what we're going for, but it does need some improvements, and that's what we aim to do. So here is our intended and final design. The braces on the user's wrist are connected to the backpack with tubes, and then the backpack contains all of the necessary components needed for our system to work. The air tank is the air supply for now, and it is connected to the brace, or is connected to the backpack, with another tube. Moving into the design of the pneumatic system is meant to inflate the brace and provide protection and support for users during fall. Going into the diagram, our system starts with an air supply. For us, we're using an air tank. This allows air to flow through the 1/4 of an inch tubing and into the valve. Once a fall is detected, an electronic signal is sent to the valve and it's then open. This allows air to flow through the valve, through the 1/2 inch tubing, and all the way to the device. After 1/2 second, another signal is sent to the valve and the valve is then shut. By this time, the brace should be fully inflated before the user impacts with the ground. Getting into some more specifics, we did testing in a range of 15 to 40 psi in the air tank because we wanted a very effective inflation time. Looking at the picture below, you can see the inlet is a pretty simple design. It's simply a quick disconnect fitting from the air tank directly into the solenoid valve. At the outlet, it's been fitted with 2 streams of airflow to allow for 2 braces to be inflated simultaneously. We've also done experimentation putting a deflation valve on the brace for better reusability. Moving into some calculations we did before the build, the most effective one was using the Darcy-Weisbach equation, which calculates pressure loss due to viscous effects of fluid flow. Originally, our design was intended to be using all 1/4 of an inch tubing. If you see that line in the middle, at a 1/4 of an inch, there's pretty significant pressure loss. Looking at that data, we were concerned that our system wouldn't have enough pressure to push the air effectively all the way to the brace. Therefore, we started looking at larger line sizes. Looking at that bottom line at 1/2 of an inch tubing, that's already a significantly better and more manageable pressure loss. This is why our design is a compromise. 1/2 of the system is with a 1/4 of an inch tubing for very easy connection with the air tank, and the other 1/2 is 1/2 of an inch tubing from the solenoid valve to the braces to try and mitigate this loss. In the end, that gives us a very manageable pressure loss across the system, as you can see in that top yellow line. This meant that going into testing, we knew that our brace would inflate effectively and quickly. Okay, so jumping into the design for the actual brace, as Melissa mentioned, our designs were driven by a lot of research at first, and here we found some of the more serious points of vulnerability across the wrist, and that really drove the engineering for this brace design. So what that ended up being was an 8-gauge vinyl layered with cotton for both comfort and aesthetic, and that was fit with that 1/2 inch tubing that Brigid was just discussing. We sealed these layers of material with alternating layers of both polymer and fabric glues, and then I also applied heat on top of that to make sure that we were reaching that optimal seal integrity. As you can see in the bottom left corner, Melissa's has these arm straps on, and that really ensures that the tubes do not restrict the user's movement, and it also helps us create that universal sizing that we were going for. One of the major issues that we ended up having was when we were attempting to put in a deflation valve. Unfortunately, this was in the later stages of our brace manufacturing, so it wasn't something that we could accommodate without sacrificing that seal integrity. So that's something we chose to omit for this iteration. So jumping into some testing, throughout the process, of course, we wanted to say, does this brace even work? So we did some rounds of testing that first started off with some zucchini benchmarking. Essentially, we dropped two zucchinis off from a controlled height, one within an inflated brace and one without a brace. And as you can see, the one without the brace ended up breaking. So we knew that this was something that was creating some protection. Later on, when we were doing brace manufacturing, we wanted to make sure that we weren't having any holes that would compromise the integrity of the air supply. So, like a bike tire, we ended up finding some bubbles and finding where those vulnerabilities were. And then finally, in the later stages, once we had built a brace that we were happy with, we wanted to go and see if others felt the same. And so we tried it on to some of our friends, family, and we saw that overwhelmingly users did feel protected and safer and felt that they weren't prone to injury should they fall on top of the brace. So finally, some brace specifications. What we ended up settling with was a successful test at 35 psi in the chamber pressure. And keep in mind, while the chamber pressure is pretty high, the brace is still at atmospheric pressure, so we're not putting our users at risk. This led to a 0.5-second inflation time, and that's really optimal for making sure that the brace has inflated fully before the person has hit the ground. We also included a zipper seam for both removability and reusability, and that also helps us meet that goal of creating a universal sizing for both men and women of all shapes and sizes, and it fits everyone.
We're now going into the final component of our prototype design, and this includes the sensing. So the hardware components which are in our sensing unit include an Arduino Nano, an MPU 6050 gyroscope and accelerometer, combined with a relay which connects to our solenoid. It also consists of two 9-volt battery sources connected to a switch to be powered on and off. The MPU 6050 consists of calculating accelerations across the X, Y, and Z axis, and also calculates the angular velocity across the moment of the X, Y, and Z axis. Throughout our project, we've transitioned with our definition from how we want to have modularity in the system. Before, we used to have 2.4 gigahertz NRF modules with multiple microcontrollers, but now we've moved to a more central hub system where all the components will be put in a backpack. And with this, we'll also be able to limit irregular movement from the user. All these components have then been integrated through soldering onto a PCB board, and this entire setup now sits in a housing unit. Past prototypes included a housing unit made out of cardboard, but our final design is now 3D printed. This entire housing unit then sits and is glued with adhesive on an acrylic backplate, which has been laser cut, and all of that then goes into our backpack as seen in the bottom right corner diagram.
Alongside researching falls, we wanted to run our own fall tests in order to improve our fall detection. In this test run, Brigid will be going through 5 different movement types, and the 2 graphs on the right will be showing the acceleration and angular velocity readings from our sensor setup from the time of this run. So to go over some of these movement types, here as she sits and then stands, those are met with high peaks in acceleration values. Walking and especially jogging is more erratic and are met with higher angular velocity values. Here she is bending over, and then finally the fall, which has the highest peak for both acceleration and angular velocity. So some quick analysis of this data, it shows that different movement types are clearly distinguishable as seen in the graphs, with more controlled motion highlighted by low angular velocities and higher velocities indicate uncontrolled motion. And the data seems to show that acceleration is greater than 1.6 Gs and angular velocities get greater than 120 degrees per second point to a fall. And additional testing such as this helped cut out false positives, negatives, as well as potential edge cases. To go over how we implemented our algorithm, it goes through 4 main cases in order to determine a fall. The first being the deviation from a base orientation, which is custom to every user. When this example user is standing straight, the z-axis would be considered their base orientation, and any angular movement forward, backward, or to the sides away from this orientation is detected. If the user deviates past a certain level, the algorithm moves forward to case 2. Case 2 differentiates between rising and falling, and is meant to minimize false positives. In simple terms, if the user is rotating towards their standing orientation, they're in the process of standing, and if the user is rotating away, they may be falling, and the algorithm moves to the final cases. These two cases check the acceleration and angular velocity sensor readings, and if both surpass our determined trigger values, the algorithm detects a fall and actuates the device.
Now, putting our algorithm and hardware components together, here's a small-scale demo of it in action. As you can see, an accelerometer is placed on top of a breadboard, and as the breadboard falls to the ground, a green light on the Arduino indicates that a fall has been detected. Notice how this light turns on before the Arduino and the breadboard hits my hand, which is a key feature needed in our prototype to make sure that the fall is detected before the user hits the ground. With everything put together, we're now proud to present our final demonstration of our prototype. And over here, you can see our test user, Melissa, running and falling down, and the entire device being able to inflate and understand that a fall has been detected before the user hits the ground. Additionally, you can see in the pictures to the side that the differences of the wrist impact based on whether it's deflated and inflated, as well as the system being able to know when to inflate. While she's running, it's not, but once she falls, it inflates.
With that, we're so proud that we created a product that does meet our goals, and more specifically, hopefully can contribute to a lot of users of all ages feeling more of a sense of independence and feeling like they've got a little bit more control over their active lifestyles, since that's such an integral part of keeping our bodies and our minds healthy and safe. So upon reflection, we wanted to create a couple of different future projects that could contribute to that goal and continuing to create a safe environment for all users to remain healthy and active. So those are here, and as mentioned before throughout the presentation as well. And with that,
To go over how we implemented our algorithm, it goes through 4 main cases.
Okay, so with that, that concludes our presentation. We want to give a big thanks to Professor Russo, Professor Gutierrez, Professor Hauser, and Professor Grace for all their help throughout this process, and thank you for joining us today. Questions if you have any. We asked some of our classmates and peers, not just friends and family, who would be like, "Oh yes, of course." We asked a bunch of random classmates to be like, "Can you put this on? Do you feel safer?" Not that they'd have a personal stake in our project, so we got some good benchmarking. So these graphs, Kyle couldn't join us. He did a lot of his calculations, but he did include some information should this question come up. And we did do some research, and we did see how that would go with our width as well. Do you know a little bit more about that?
Basically, just on a simple level, we know that the brace having air in it is going to slow down the impact time, or it's going to increase the impact time, which therefore decreases the force on the hand, because the impulse has to stay the same if you're falling and stopping. It doesn't matter if the brace is on or not, it's the same level of impulse. I went to the wrong slide. We had considered material properties, obviously, and we did a bunch of fall tests, and we never had popping in the vinyl. That is also something that we would think would be a really good next project, would be material selection, because we didn't spend as much time on that as we wanted, because we wanted to keep iterating on prototypes. But that would be a really great next phase, is to see which materials would have enough stretch that they definitely wouldn't pop. Great, thank you so much. Thank you.